Welcome again to a lecture of the course on audio signal processing for music applications. Until now, we have been analyzing sounds using sinusoidal representations. They work, but there are many types of sounds that are best described by what we call stochastic models. Signals like the sound of the ocean or the boat noise of a violin fit into this category of stochastic signals. We will talk about this today. We will first introduce the concept of stochastic signals, then how to model them, what is a model of an stochastic signal, and then more specifically on how to deal with sounds using these models, so how to approximate from an stochastic perspective a particular sound. And finally, we will describe the concept of a system that can perform analysis and synthesis of sounds using these models. The stochastic model is complementary to the models that we have covered until now. In fact, in the following lecture, we will combine the stochastic model with the sinusoidal-based models, and we'll be able to take advantage of the best of both types of models. What is an stochastic signal? Well, a stochastic signal cannot be described in a deterministic way. It can only be described probabilistically. And the field of statistical signal processing deals with this type of signals, and it's a quite advanced topic. Here we'll give a very broad approach, which is sufficient for our needs. So in a statistical signal processing, we talk about the loss of probability as a way to describe these stochastic signals. And we talk about the mean, the variance, and the probability distribution of particular signals. And there are some mathematical functions that are used to analyze these type of signals and capture some of its characteristics. For example, one is the autocorrelation function. We have already seen this function before. The autocorrelation function allows us to measure the periodicity of a signal or the degree of repeating patterns in a particular signal. We use it for detecting the fundamental frequency. So this is a function that can be used to measure how stochastic is a signal. If there are no repetitions, that means that it's going to be close to a stochastic signal. So the lower the autocorrelation function value is, the closer is going to be this signal to a stochastic signal. And another mathematical function that we can use is what is called the power spectral density. And also we have seen a similar version of that. It's basically the DFT, but with a major difference. Is basically the DFT to the limit. We take the square value of the absolute value of the DFT, and we take n, the size of the DFT, to infinity, and if it converges to a function, that's our power spectral density, and that happens in quite a few signals. And there are many models that have been proposed to deal with this type of stochastic signals. We will use a very general model expressed by this equation, which is in fact the convolution of two signals. So we will consider as an stochastic model the idea that a signal can be expressed as the convolution of white noise with the filter approximation of our signal. So by taking this convolution, we are assuming that the signal that we are dealing with is well expressed or well represented by its impulse response. If we look at the same equation from a spectral point of view, we can understand a few more things. So a convolution in the frequency domain is the product of the two spectra, so the product of the white noise, the spectral of the white noise with the spectrum of the impulse response of the filter. And if we express it in polar coordinates, then we can express it as the product of the two magnitude spectra and multiply by the exponential e to the j and the sum of the two phase spectra. Okay, so that's the product of these two spectra. And if we consider that this is a stochastic signal, we basically can say that the magnitude spectrum of white noise is a flat line, and we will see that a little later. So it's a constant, so therefore we can take it out of the equation, so we can reduce the concept of the impulse response of the filter of the input signal by the magnitude spectrum of the input signal, an approximated version of that, which could be the frequency response of a filter, or it could be some other type of function, but a function that approximates the magnitude spectrum of the input signal. And as the phase of the model, we use the phase of white noise, because the phase of an stochastic signal is not so relevant. Therefore, we just can reduce the phase representation of our signal with random numbers, with the random numbers of the white noise. Okay, so this is a good way to express this stochastic model. So we take an approximation of the magnitude spectrum of our signal, and we take random phases for the modeling the phase spectrum. So this is an example. So if we start from a fragment of the sound, for example, of an ocean sound, and let's listen to that. Okay, so we just take just one frame of that, and then we compute the magnitude and phase spectrum of this ocean sound. So the red plot is the magnitude spectrum of our input signal, and the phases, the cyan function, is the phases of the input signal. And then the black line on top of the magnitude spectrum is the approximation of this spectrum, and we'll talk about different ways to approximate that. So it's basically a smooth approximation to the magnitude spectrum, and the black lines in the phase spectrum are basically random numbers. Okay, and we claim that these random numbers are an approximation or a model of the random numbers that in fact are in the ocean phases. So we are basically saying that the phase spectrum of the ocean sound are just random numbers and can be approximated with any random number sequence. Okay, and then if we take the inverse Fourier transform of these two black lines, of the approximation of the magnitude and the random phases, we get this output signal, and we are claiming that perceptually this signal is going to be similar to the first one. Of course, by looking at it, that might not seem to be the case because it's clearly a different shape, but given that we're talking about stochastic signals, the details of the shape are not relevant. What is important is the statistical properties, and so we will be able to try to prove if this type of approximation works. So the main analysis issue for this stochastic model is the approximation of the time varying magnitude spectrum of the input signal. So we'll have to compute this approximation at every frame. A common approach for obtaining a filter that approximates the spectral characteristics of a sound is to use linear predictive coding. With LPC, with linear predictive coding, we can obtain a set of filter coefficients, A sub k, and the frequency response of the resulting filter approximates the spectrum of the input sound. So here we see a signal x, and the idea is that the approximation of this signal is defined according to this LPC model as the linear combination of past samples. Okay, so it's as defined as the sum from k equal 1 to capital K of a sub k multiplied by x of n minus k, which are the previous samples. This is basically the expression of IR filter, an infinite impulse response filter. That is a linear combination of previous samples. And then the goal of LPC is to find these coefficients, to find a sub k that best approximates x and generates a similar signal x hat. So we define an error function that is the sum of the square root of this the original signal with this approximated signal, and we sum originally from minus infinity to infinity. Of course, then we will narrow down to finite length signals. But with this error measure, basically we can try to identify the A signal, the A coefficients that minimizes this error signal. Okay, we will not talk about how to actually implement that, but this is a very common approach for obtaining these coefficients, and therefore for doing what we call the LPC approximation. So if we start from a sound, for example, of a voice sound like this soprano sound that we can listen to. In fact, this is a type of sound that is commonly approximated with an LPC model. And what it does is obtains this black line that we see in the bottom plot. So in the bottom plot, we see the magnitude spectrum of this fragment of this voice, and the black line is the magnitude spectrum of the approximation of this LPC filter that approximates this signal. And as we can see, it kind of approximates what is a very common characteristics of the voice, which is these formants, so these resonances. So an IR filter is a way to approximate the resonances of a signal quite well, and so the LPC works quite well for these type of signals. But the LPC does not work so well for many other types of signals. In here we present a more simpler approximation that is just based on low-pass filtering. And we show it by implementing a low-pass filtering using the DFT. So we start from a signal, A of k, and then we take the DFT of that, and we low-pass filter. Low-pass filter means basically we cut the spectrum, and we only accept the lower part of that spectrum. And then we can take the inverse DFT of that, and we get another signal, which this A tilde is an approximation, a smooth approximation of the original A sub k signal. Then we might need to extend the signal in order to generate the same number of samples, or the same so at the same sampling rate that the signal that we started with. So in order to do that, we might have to take the DFT of that, zero path to extend it to a longer FFT size, and then take the inverse DFT of that. So then B of k is of the same length than A of k, because the A tilde is just an approximation, has less samples, which is good because that means that we have an approximation with few number of samples. These coefficients, basically this A tilde is just the coefficients of the approximation. And this is going to be the approach that we will use in our implementations. So now let's talk about the synthesis part of the stochastic model. If we approximate a sound using LPC or with any other type of filter design approach, we can synthesize a signal from the obtained filter coefficients by filtering white noise. So this equation that we already have seen before is the implementation of an IR filter, in which we are filtering white noise. We are filtering the signal U with a series of coefficients A sub k that are the coefficients of the filters. And the implementation of this equation can be done in different ways. For example, these two block diagrams are two different structures that are used to implement this type of filtering. One, the top is called the direct form structure, and the bottom one is the lattice structure. But if we obtain an approximation using the low-pass filtering approach that we mentioned, we can synthesize the sound directly by computing the inverse DFT. So in here, we start from our approximation of the spectrum of the original signal, which is basically this smooth version of the signal. It's kind of like what we said, the low-pass filter approximation of the signal. And then we can just take random phases, the phases of the white noise, and we take the inverse DFT, and that's basically going to be a filtering operation of white noise. Okay, so we start from the smooth approximation of the signal, the random phases, and then we take the inverse DFT, and this will be the method that we will use in our examples. So now let's put it all together into an analysis synthesis system using this stochastic model. And so here we see the block diagram that we will be implementing, in which we start from the signal x of n, hopefully a stochastic signal. We compute the FFT, we take the absolute value, and then we do this stochastic approximation, which is again this idea of low pass filtering, so approximating the magnitude spectrum with a smooth curve. And then we can do the synthesis. The synthesis will be done by doing this inverse FFT of this stochastic approximation that might have to be zero pad, and so to interpolate it to be a longer size spectrum, and then we generate random numbers for the phase spectrum, and we can take the inverse FFT of that, and that will return a fragment of a sound. And then we can just do an overlap add, similar in this exactly same way that we did for the sinusoidal modeling. Here also we will have to take care about some smoothing windows so that the overlap add works correctly. But with this we can reconstruct the original signal. So let's listen to some example. Okay, so this is the ocean sound that we played before. And then the first is the magnitude spectrum, the absolute value of the spectrum of the whole, so the spectrogram of this whole sound with a particular window and FFT size and a hop size. And then the stochastic approximation is basically a visualization of these coefficients that are much fewer. So in fact here we took kind of a compression of 0.1, so every 10 samples of our magnitude spectrum we reduce it to 1, so that's the idea of the approximation. And then we can synthesize by combining this magnitude spectrum with random numbers. So let's listen to the synthesized results. If you do an A-B comparison with the original ocean, it sounds different, but it clearly sounds like an ocean sound. So for stochastic signals, maybe it's not so relevant to reproduce the exact characteristics of the sound, but basically these kind of general characteristics of the sound. And this is what this approach does. So the field of statistical signal processing is quite an advanced topic, as I mentioned. And most of the references, in fact, are quite complicated, are quite advanced. If you start by looking at these Wikipedia pages, you can get links and descriptions to all these more complex view of stochastic processes and statistical signal processing. So feel free to go there and check all these topics. And that's all. So we talked in this lecture about stochastic models. The goal was to introduce a strategy with which to model some sounds or parts of sounds that cannot be well represented with sinusoids. In the next lecture, we will see how we can combine these stochastic models with the other models we have been discussing, the sinusoidal based models. So I see you in the next lecture. Bye-bye.